Welcome back. In this module, we're going to be looking at the logarithm function. Recall from the previous module that if y equals e to the power of x, then x is defined to be the logarithm of y to the base e, commonly written as ln y. From the module on inverse functions, this means that the logarithm function y equals ln x is precisely the inverse function of the exponential function y equals e to the x. Recall the cancellation property for mutually inverse functions, which states that the application of a function and its inverse, in any order, results in the original input being recovered. In other words, f and f inverse effectively cancel each other out. You may recall that the example we used at the time to motivate inverse functions were the doubling and halving functions. Applying the cancellation property here, we get the following two identities, which states that the exponential and log functions effectively cancel each other out. Specifically, the first identity states that exponentiating an input x, followed by logging the result, results in the original x being recovered. The second identity does the operations in reverse. That is, we log the x first and then exponentiate, and this also results in the original x being recovered. We can use these cancelling properties to help simplify algebraic expressions involving logs and exponentials. Consider the example e to the power of 2 log x. Using the third log law in reverse, we can make the 2 jump inside the log. Then using the fact that the exponential and log functions cancel each other out, the entire expression simplifies to just x squared. We can also use the cancelling property of logs and exponentials to help us solve equations. Consider the following example, e to the power of 2x minus 3 equals to 7. Notice here that our unknown variable x is in the power of e. So to isolate x, we must first somehow get rid of the base e. And since log and e cancel each other out, our first step is to therefore log both sides. Then solving for x, we get the following. Here's a final example of using the cancellation property, which involves the exponential model we used in Day 8 to simulate population growth in an outback town. Recall that this model gave a population of 1,000 people in the year 2000, roughly 7,400 people in 2010, and an estimate of roughly 55,000 people in the year 2020. In other words, by varying the independent variable t, we could calculate the population at any year of our choosing. But what about the reverse situation? That is, choosing a population and asking at what time t will that population occur? For instance, when will the population reach 1 million people? Here, we must set the population p to be 1 million in our model, and our goal is to solve the equation for t. To isolate the t, we must first cancel out the e in our way. Therefore, we log both sides. Dividing both sides by 0.2, we thus get t to be roughly 34.5. In other words, the population should reach 1 million people by the middle of the year 2034. You should now pause the module and have a go at these practice questions. All of these questions are designed to train your skills in applying the cancellation property of logs and exponentials to either simplify expressions or solve equations. Here are the answers. Finally, recall from the module on inverse functions that the graphs of two mutually inverse functions are symmetric about the diagonal line y equals x. Therefore, by reflecting the graph of the exponential function about the line y equals x, we obtain the graph of the log function y equals ln x. There are at least three important things to note from the graph. Firstly, the y-axis forms a vertical asymptote for the function. That is, a vertical line to which the graph approaches closer and closer as x approaches 0, but never quite touches. Secondly, the function isn't even defined for negative x values or for when x equals 0. And thirdly, the graph intersects the x-axis at the point 0, 1. Alright, here's a summary of what we've learned in this module.